Well, I am here as coordinator from the ICRM LLMT working group. My aim is to give some inputs about the applications where the main interest of mass spectrometry can be placed in our community. Some of these applications has been already presented very nicely in the previous presentations. The common point of those were that radionuclide concentrations were the objective of the final objective of the measurement. Maybe because of my experience, I will focus in those that use the radionuclides as a tool to other studies. So, okay, first I would like to present what is the International Committee for Radionuclide Metrology. This is made of radionuclide metrology laboratories all over the world. It was started in 1974, and now at present there are 20, sorry, because I don't see the number, I have to move this to another place. Okay, 47 member institutions. The purpose of this committee explicitly is to build a forum, an international forum for the dissemination of the information on techniques, of course, development of techniques, but also this dissemination out the frame of reference laboratories that make the ICRM. So for this, ICRM organized a general meeting every 3 years, well, depending. Last was in 19 here in Salamanca, and the next one will be in 23 in Bucharest. But this was due to COVID issues. So, okay. Sorry. The different fields of interest are dealt with in 8 working groups into the ICRM. Each of these is dealing with one technique, mainly, except the first one, which is general radionuclide metrology techniques. Among all of them, there is one, the low-level measurement techniques working group that whose purpose is to study those techniques capable to determine accurately low activities of the radionuclides used in a wide variety of applications. This means that as we deal directly with the applications, we get to attract some other laboratories not belonging to the ICRM to our meetings that are also organized in this case, 4 years. Okay, when we talk about low-level techniques, we are talking about a wide variety of radiometric techniques, from alpha particle spectrometry to ultra very low-level background gamma ray spectrometry, when more work had to be done to reduce the background, the detector background. But not also radiometric techniques are included, also mass spectrometry. So there is a specific topic in our meetings dealing with these non-radiometric techniques. Applications can go from fundamental physics experiments, for example, those with the more stringent requirements as neutrino physics, to environmental studies, that can have a very wide range of activities. I have placed a number here on the screen. 1 becquerel per gram, okay, is maybe high for some of you, but we are talking about environmental radioactivity. So there is they can be from this amount to very much lower amounts. And this is in this lower amount where we found our challenge. Okay, maybe I will not go into the details of the techniques as much as my colleagues in the previous presentations. I will just focus, as I told at the beginning, to give some inputs of interest, of interesting applications that where mass spectrometry can be really very useful. For me, the most where is still a lot of work to do is in all these applications that use radionuclides as a tool. Among these, all that use these radionuclides for building chronologies are the ones that more impact can have in several, in a wide variety of studies, like, for example, climatic change, sustainability of groundwater resources in dry regions, human evolution, anthropogenic effect in marine coast and fishing resources. All these applications needs a wide range of chronologies. So there are several radionuclides that cover the most of the ages. And also there is a wide range of matrices in where these radionuclide concentrations are measured. Okay, here is a list coming from the young to the older ages. Here we can see us for the last 200 years when you want to study the anthropogenic effect in some environmental systems, as the coasts are, lead to 10 related to 226 radium is the main radionuclide to give these ages. So we go from up to reach carbon-14, which is the most famous. We need also another radionuclides to cover this slot of this time slot, which is silicium-32 in the last 1,000 years, radium-226 even for the last 5,000. And then we found the famous, as I told, carbon-14. So, okay, we need to go to all these ages, and we can get it with the ratio between potassium 40 and argon 40. And then finally, we got our thorium-230, uranium-238, also 232 thorium, which is needed for this chronology, which is the ratio that goes farther in time. Of course, we can find another ratios that are interesting in different fields, as the ratio 234 uranium to 38 uranium to date groundwaters. Also protactinium to 31 to 35 uranium ratios to measure oceanic streams, also to compare with the 230 thorium to 38 uranium chronologies. or to study volcanic rocks in the Holocene, radium-226 related to thorium-230, and at the end, aluminium-26 for the meteorites studies. What kind of matrices are the ones that we need to measure in the different topics? This well, can be in some way classified according to the dating technique. Some of them can be very different among in composition. For example, for lead-210, we can get sediments, speleothems, corals. In the case of silicium-32, this can be measured in specific marine species with high silicium concentrations. But if we go up to 30 thorium, to 38 uranium, this chronology method is used also as in a wide variety of samples, from oceanic sediments to corals, speleothems, and waters. So, okay, the main common characteristics of these samples or matrices is that all of them are natural matrices, and all of them can have very different compositions. Laboratories dealing with these matrices has to be prepared to handle with this with different methods, pretreatment, treatment methods, and of course different techniques. Okay, as these radionuclide measurements are used as a tool for another studies, the point is that in most of the cases, the laboratories making these determinations belong to university departments or research institutions that are not in the orbit of the for example ICRM, which are not devoted to measure environmental radioactivity as a purpose. But they provide results that should lead to a high accuracy chronology. So in most of the cases as well, they use mainly radiometric techniques. They can go from mainly alpha spectrometry, because we are dealing with heavy radionuclides, so mainly disintegrating by alpha particle, but also use gamma spectrometry and liquid scintillation, etc. In some cases, they also have, through the university services, the possibility to reach a mass spectrometry, but in general, it's a conventional mass spectrometry. So, okay, here I have written some of the numbers important for us, which correspond to the limits of detection. This limit of detection, in general, for these techniques, range in water between 0.2, 0.3 becquerel per cubic meter. For uranium-234, uranium-238. In organic samples, we are talking about rocks, soils, sediments. The range is wider. Also, the radionuclides of the heavy radionuclides of interest, which is. And these values go from 0.5, 1.5 becquerel per kilogram. The point here is that these values are very are the ones that we can find in our chronologies, in the matrices that we are measuring for these chronology purposes. So in most of the case, we are measuring at the limit of the technique. This means large uncertainties, and this means also, maybe a lack of reliability. For this reason, reference materials, intercomparison exercise could be very could be key in the application, or in assessing the reliability of the results given for laboratories in this field. Okay, I'm not talking about carbon-14 laboratories, because they have their own community, very well organized, with very clear rules, also methodological rules, and they control in some way the results provided for the chronology. So in this, when we are dealing with carbon-14, we need to be inside the community. But this is not the case for the other chronology. So we are focusing in these other cases. So just to give an example to know what amounts we are talking about related to the radionuclides of interest. I have not talked about sample amounts, I mean sample masses needed. I go to the most, let's say, extreme or stringent sediment, sample, which is the sediment coming from a core, a sediment core, 200 meters. Let's figure out what kind of core you need. The diameter has to be very small in order to go so deep. And then if you need a high precision chronology, you need to, let's say, to cut the core in slices, which at the end weight 10 grams, for example, in total. So for measuring these samples, you can handle 5 grams of sediments in most of the cases. Sorry. So with this in mind, if we need to go to values that are around the minimum detectable activities in radiometric techniques, uranium can be 0.7, 0.5, depending if it's 238 or 234 uranium. In case of thorium, you go to a little bit higher values for thorium 230. This means in number of moles per kilogram, we need to go to 2.4, so to techniques sensitive, to amounts of 2.4, 10⁻⁷, in the most in the better case, which is the uranium 238, or to go to 5.7 minus 12 mole per kilogram in thorium-230. So the point here is could metrology laboratories develop reference materials using mass spectrometry with this radionuclide concentration? Of course, this should be done in environmental matrices, and also the materials provided should be the original ones, could not be processed for this. So, okay, that's all. I have been short. Thanks a lot for your attention. I would like, of course, acknowledge to all my colleagues in the low-level technique group. And okay, I'm ready for your questions.